Hello guys, today I'm going to explain about physics of a TOPCon solar cell. So I am Pinal Rana and let's begin with the topic. So let us first start from the basic. So for manufacturing a solar cell, any kind of solar cell, we need a semiconductor. So uh, in atmosphere or in nature, there are two basic semiconductors and a star of the semiconductor compound. So the two basic semiconductor are one is silicon and second is the germanium. Silicon has an atomic number of 14 and germanium has atomic number of 32. So based on the atomic number, this is on left hand side I have shown the different energy level. So 1s2, 2s2, 2p6, 3s2 and 3p2 is the energy levels of the silicon, and these are the energy level of a germanium. So in the industry, we generally use the silicon based semiconductor. Why? So it has two main reasons. One is silicon is the second most abundant material found from the earth crust. That's why it's relatively cheaper than the germanium. If we compare the cost of silicon, which is around 1.45 to $1.48 per kg, whereas germanium is very costly, costing us around $3,000 per kg. However, germanium provides a better or higher uh, conversion efficiency of a solar cell than the silicon. Therefore, for the space applications, we are using germanium because it provides higher efficiency as high as 68 to 70%. Whereas silicon is commercial silicon that is available. Commercial silicon solar cell that is available in the market is provide higher efficiency of around 25, 26, 27%. So all the commercial purpose for all the commercial purpose we are using silicon based solar cell, whereas for this particularly space application or high-end application we are using germanium based solar cell. So let us first understand the structure of the solar cell. So based on this energy caps, energy level, uh, from this we can understand that uh, at the valence band, or we can say it at the outer electron band, there are for p level it has to be a 6 electron, but for the silicon at the p level there are only 2 electrons, so there are shortage of 4 electrons. Therefore, if you see, because of this shortage of 4 electrons, it creates or form bonds with other elements. In this case, we have shown the bond between silicon and silicon. So here we have shown this one electron of each silicon form a bond with one electron, four different electrons of a different silicon. However, if you observe over here, the silicon present at the surface may not create a bond with the surface adjacent silicon, which leads to the formation of a dangling bond. So this dangling bond is behave as a recombination center, which reduce the performance of a solar cell. Therefore, our main aim in the solar cell is to reduce this dangling bond. Now, in order to reduce this dangling bond, we are depositing different types of dopant uh, based on the type of silicon. So here we are going to discuss the only TOPCon solar cell. So for TOPCon solar cell, generally N type of silicon is used. Why we are using N type of silicon for the TOPCon and P type of silicon for the POC solar cell? That is the another question raised by the different uh, people. So definitely we can also use the P type of silicon for the TOPCon and N-type silicon for the POP. But here, this is the most common practice by the industry. Why this is the most common practice? Because P types of silicon produce is easy to produce and it is less costly. Then why we are using N type of silicon in TOPCon? Because if you use N type of silicon, it is relatively costlier than P type. However, this cost is compensated by the extra or additional efficiency that is produced by the solar cell. That's why we are using N type of silicon in TOPCon technology. For the manufacturing of TOPCon, manufacturing of N-type silicon is costly. Plus, it is also very environmentally hazardous. It creates toxic gases. Therefore, it requires much more controlled environment and much more sophisticated equipment, which leads to the in, leads to higher fabrication cost of N-type silicon. However, this cost is compensated by providing extra efficiency that is able to produce by the N-type silicon. So if we have an N-type silicon base, then we have to deposit P-type uh, uh, emitter to form a PN junction. Once the PN junction is formed, the depletion region is formed at the PN junction. What is this depletion region now? The depletion region is basically uh, no free electron and holes zone where only the neutral atoms are present. So when elect where the when the light is incident on the silicon on the PN junction diode, it passes to the P-type emitter and reaches the depletion region. Because of here, we also observe here why the P-type emitter thickness is smaller compared to N-type. This is mainly because our main aim is to reach more light to the depletion region. So if this thickness is high, light will not reach to the depletion region. That's why by giving the smaller thickness with highly doped P-type emitter, or we can say boron dope, it is possible to reach more sunlight to the depletion region. Once the light is reaches to the depletion region as shown in figure over here, it creates more free electrons and holes. So initially the bottom silicon is the N-type. So because of this N-type here, a positive charge is generated and this is the P-type. Therefore here negative charge are generated. Now when the sunlight reaches the depletion region, because of this uh, driving force of N and P, whichever the holes are generated is moving towards the top side, and whichever the electrons are generated is moving towards the downside. That's why holes is moving up and electron is moving downside. Now let us understand how this uh, electron and hole moving in different direction using driving force, and let us understand using band gap energy diagram. So for the TOPCon solar cell, this is a p-type emitter and this is n-type base. Now let's take a small strip over here and rotate anticlockwise by 90 degree. Now if we compare the um, band gap diagram for this p-n junction, this is how it looks like. So p-type has a higher energy band gap than the n-type. That's why it is showing relatively at higher height than the n-type. And this transition is called the depletion region. So at the surface, these are the dangling bonds or surface electron or silicon or dangling uh, bonds we can see. So uh, from so let's say at the higher, so let's say at the valence band when the electron and holes pair are there, when the electron sunlight is incident, electron is absorb the energy and moving from valence band to conduction band. So at the conduction band there are various energy level based on the material. Now we have to assume that we have to consider that holes are behaving as a helium balloons and electrons are like a solid ball. So electron is always moving towards downwards and all holes are always moving towards upwards. So this is a band gap diagram of this p-n junction. Okay. Now in the TOPCon solar cell at the rear side we are depositing the tunneling oxide layer of a silicon oxide. On top of that we are a polycrystalline silicon layer. So why we are adding a polycrystalline silicon layer at the rear side? That is mainly because it's from N minus junction. This N minus junction will further reduce the energy band gap, so that from here, instead of recombining the electrons, it will further move down, and here hole will further move up. This will it reduces the surface to surface recombination losses and improve the box solar cell performance. So in this slide, I have shown the structural difference between the box solar cell and TOPCon solar cell. So as I explained earlier, box solar cell uses p-type silicon base, whereas TOPCon solar cell using n-type silicon base. In box solar cell, at the rear side, precision layer plus capping layer is used, whereas in TOPCon solar cell, silicon oxide tunneling layer of 1 to 2 nanometer with polycrystalline dope silicon is used at the rear side. Further, in some cases, the silicon nitride capping layer are also used. So why here in box solar cell they are using aluminum oxide and silicon nitride capping layer? The reason is mentioned here. The aluminum oxide layer enhances the light trapping by acting as a part of the reflective coating. This ensures more sunlight is absorbed by the silicon wafer rather than escaping through the rear side. There, because basically to reflect the solar light from the rear surface. So when the solar light is coming, it's passes or transfers to this rear side. Therefore, to reflect the solar light from the rear surface and produce more free electron, we are using this aluminum oxide silicon nitride capping layer. So here I have explained the details of the capping layer. Reduction in the conventional losses, enhance the light trapping, and these are the other difference advantages that provides the capping layer in power solar cell. Further, here I have shown the comparison of TOPCon and power solar cell. So, if we compare in terms of light induced degradation, so box solar cell suffers from the light induced degradation because of the boron oxygen defect, whereas in TOPCon solar cell there is no light induced degradation because there is no boron doping, whereas in box solar cell this p-type solar cell has a boron doping which leads to the boron oxide defects. For the efficiency, our box solar cell is limit to 23 to 22 to 24 max, whereas a TOPCon can easily reach to 25% efficiency. So here in box solar cell, minority carrier lifetime is shorter, whereas in box solar cell, minority carrier lifetime is shorter, whereas in TOPCon it's longer. Cost is historically cheaper. This is slightly more expensive, but currently R&D is going on in TOPCon, so hopefully it will reduce in near future. If we talk about the stability, moderate degradation over time, whereas better stability and longevity. Here I have explained different types of layer used in TOPCon along with its advantages. So in TOPCon we have used the 1 to 2 nanometer thickness of tunneling oxide, which acts as a potential barrier for the charge carrier for both electron and holes, and quantum it's allow the quantum tunneling of electron to pass through its extremely thin layer, whereas the polysilicon layer align energetically with the silicon substrate, enabling carrier selectivity. So what mean by the carrier what I mean by the carrier select, so it's only allow the electron or majority carrier to passes through the tunneling oxide and tunneling oxides and extract the polysilicon extracts in the polysilicon layer, whereas it's block the holes which who is the minority carrier lifetime also, minority charge carriers also. Here are the other use or purpose of a tunneling oxide, explaining its physics using the fishbone diagram. So here further what is the purpose of tunneling oxide that I explain in detail, you can read by pausing the video. This is a further use of a tunneling oxides in terms of carrier selectivity, energy band alignment, and as I explained why we are using n-type silicon is also explained here. Thank you.